Hello guys, welcome again to another video from Seafield Academy, where we strive to learn together from each other. So today's topic is Kruskal's algorithm for finding minimum spanning tree. We already discussed Prim's algorithm for MST. If you haven't seen the video, make sure to watch it on my channel. So yeah, let's get started with Kruskal's algorithm today. So again, coming back to what a spanning tree or what a minimum spanning tree is. So in a graph, it's a set of edges that together forms a tree, and it touches every vertex of the graph such that the total weight of the edges in the tree is minimized. So there are a few algorithms to find minimum spanning tree, and minimum spanning tree finds a great application, finds its use in a variety of applications. So again, Kruskal's algorithm is also a greedy algorithm where it tries to optimize at every step. So at every step it tries to see the minimum possible weight of the edge to be chosen, and it adds it to the tree. So it differs from Prim's algorithm in a way. In Prim's algorithm, the idea is to add a vertex to the current tree, but here the idea is to add an edge to the current tree or the existing forest that we have, starting from the minimum possible edge. At every step we pick the next cheapest edge possible and add it to the existing set of edges, and we keep on doing that till we end up with our spanning tree, which covers all the vertices. So here is an example where you can see the minimum spanning tree is highlighted in red. It touches all the vertices and it's a tree, which means it doesn't have any cycles. So a little bit about history of minimum spanning tree, Kruskal's algorithm. So as the name suggests, it was developed by American mathematician Joseph Kruskal, which was done way back in 1956. And how does it work? So Kruskal algorithm focuses on the idea of adding edges to the existing tree. So initially we just initialize a forest, or basically a blank tree, and we just choose the cheapest edge that is available and add it to the current tree. So as you can see on the right side, there is an animation from Wikipedia. So we choose the smallest possible edge, then we choose the next smallest possible edge, and we keep adding to the existing set of edges and actually expand our forest to include these edges. And slowly as we do that, we can see the tree starts forming, and we keep doing that till we are able to reach all the vertices. So the idea is pretty simple. At every step, grow the forest by adding one edge, which is the minimum edge from the remaining set of edges, such that it doesn't form a cycle with our existing set of edges. The reason why? Because if we have a cycle, then we no longer have a tree. Remember, trees don't have cycles. And we keep repeating this step over and over again till we are able to span all the vertices in the tree. So let's try it out on an example. So here is a graph which has 6 vertices, A, B, C, D, E, F, and a few edges, couple of edges with weights 2, and there are 3 edges, C, D, D, E, and E, F with weights 3, and A, B, A, C, and C, E with weight 4. So let's apply the algorithm on this graph. So first step, select the minimum edge. So what are the minimum edges we have? BC and CF both have weight 2. Now since this is a tie, we just pick one of the edges. In this case, let's say we pick BC 2 and add it to our existing forest. So we now have edge BC in our existing forest, and the total weight of the existing spanning forest is 2. Next iteration. Now the next possible minimum edge is CF with weight 2, and we'll just pick it and add it to our existing tree or the existing forest. No complications. So now we have 2 edges and 3 nodes, BCCF. Total weight of the spanning tree has become 2 plus 2, 4. Moving on now in the next iteration, iteration 3, now we are done with edges of weight 2. So we now have the next minimum weight edges are CD3, DE3 and EF3. Again there is a tie, and we just arbitrarily will choose DE this time of weight 3. We can choose anything, it doesn't matter at this stage. So we choose DE this time and we include it in our spanning forest. So our spanning forest now has BC, CF and DE, and total weight is 4, which was earlier, plus 3, so 7 is the existing weight of the spanning forest. Moving on, in iteration 4, the next few edges are CD and EF, which have weight 3, and we need to choose one of them. And if you notice, at this stage currently we actually don't have a tree, we have a forest. That's why there are 2 disconnected pieces of tree. Now as we choose the next edge CD, we will have actually a tree again, which is connected, and we could have chosen EF as well, it doesn't matter. So because it was a tie, we just chose one of the edges. And so if you notice, we have now covered about 5 vertices, 4 edges, BC, CF, DE and CD, and the weight of the spanning forest has increased to 7 plus 3, 10. Now the next iterations, as we may guess, EF is the next possible edge, which is of weight 3, to be included in our spanning tree. But there is an issue here, we cannot include this edge. Reason being, if we add it, we'll have a cycle with 4 edges, FC, CD, DE and EF. And remember, we need to find a spanning tree, and a tree cannot contain a cycle. Hence we cannot choose EF. We have to discard it and move to the next set of, or the next minimum available edge. So the next minimum available edges we have is AB with 4, AC with 4, CE with 4. We can choose any of them, but if you look closely, again we cannot pick CE, because if we pick CE of weight 4, we'll again have a cycle, CD, DE, CD, DE and CE. Hence we cannot pick this particular cycle, this particular edge CE as well. So essentially we are only left with 2 possible options, AB and AC of weight 4, and we will just pick AB of weight 4 this time. So adding AB to our current forest expands to include 5 edges now, which is BC, CF, DE, CD and AB, and the total weight, you can notice, is 10 plus 4, 14. And if we look closely, we have covered all the possible vertices on the graph. There is no vertex left, and the tree which we have is also connected. It's no longer a forest. Hence our algorithm will stop here, because we have found the minimum spanning tree that covers all the edges. So guys, we are done here. I hope the walkthrough of the algorithm made sense. I've tried to include it as an animation, but if still there are any questions, feel free to comment below on this video and I'll try to answer it as much as possible. So thanks for watching another video, and before we end, there is an exercise. Now since we have covered both Kruskal's algorithm and Prim's algorithm, if you haven't watched the Prim's algorithm video, I'll link it up here so that you can go through it. So here is a graph given, a little bit complex. The weights are a little higher side, but the algorithm process is same. So an exercise: find a minimum spanning tree using both Kruskal's algorithm and Prim's algorithm. If you have any questions, do comment up in the video and I'll try to answer your questions here. If you can post a solution as a comment, that would be great. If you have any more clarifications needed, or if you want me to cover any other algorithms as well on graph theory, I'll be happy to help you. So we'll end here. Thanks again for watching the video. Make sure you subscribe to our channel for more videos. Thank you. Bye bye.